Part C. Let's look at this example of a removable discontinuity. We have the function y is equal to x squared plus x minus 6 all over x squared minus 4. Now in this case, or in this example, we're looking at x equal to 2. Well, let's see. What is the function value when we plug in x equal to 2? Notice that that's going to be equal to 4, right? Plus 4 plus 2, which is 6 minus 6, that's 0. And of course at the bottom it will also be 0, because of this being 4 minus 4. So you have a case of a 0 over 0 situation. And then remember, when we look at the limit of x squared plus x minus 6 over x squared minus 4, and then whenever we encounter a 0 over 0 situation, we see whether we can factor out whatever makes it 0. So this is the limit of x. I guess it's x minus 2 and x plus 3, right? Okay, whole thing divided by, what are the factors of this difference between squares? Again, that's x minus 2 and x plus 2. So if when you take the limit as x approaches 2, remember when we say x approaches 2, we're just looking at how the function behaves around 2, not necessarily at x equal to 2. So it turns out that that can be cancelled, and of course this is now equal to, that is 5 over 4, or 1 1/4. Well, the problem is this function continuous? Well, what is our f of 2? We said that it does not exist. But the limit does exist, and it's equal to 5 over 4. And what type of discontinuity? It's a removable discontinuity at x equal to 2. So to remedy the situation, now we have to redefine. So what we do now is we define a function, capital F of x, say, and whenever x is equal to 2, we let it be equal to 5 over 4. And then as long as we keep the same function, okay, x squared plus x minus 6 over x squared minus 4, then that's really just equal to, that's going to be equal to x plus 3 over x plus 2. Remember, because we see that as long as x is not equal to 2, these two functions are really equal to each other. This is identical to this function as long as x is not equal to 2. Then we say that capital F of x is the continuous extension of this function that has a removable discontinuity at x equal to 2. And later on we can go back to this function once we've talked about limits at infinity. Again, here's an example of a removable discontinuity, and this is a very familiar function. Let's see. F of x is equal to sine x over x. And when we look at the limit as x approaches 0, remember that this is a theorem, and we see that the limit of f of x approaches 0 is 1. Because remember, the limit of sine theta over theta is 1. It's the same thing. We just change the variable to x. But what is f of 0? It does not exist. Oh no, it does not exist. So therefore, what do? It is a removable discontinuity because the limit does exist, except it doesn't have any function value there at the point where the limit exists. So we remedy the situation by removing the discontinuity. And how do we do that? Well, just redefine. Redefine f of 0 to be equal to 1. And there, you fixed it. So we plugged a hole where there was a hole, we plugged it. Okay, so that means this, capital F, is the continuous extension of little f. Here's a problem. For what values? Okay, problem. for what value of this letter m will make the given function continuous at every point in the domain. So basically what we've got is a combination, it's a piecewise function g, where it behaves as a parabola for x's to the left of -2, and it behaves as 3x plus 5 for values to the right of -2. There's a typo right there. So our critical point that we have to be looking at is that this function may have a discontinuity at x equal to -2. But look, if we fix the right m, then as long as the limit on both sides would exist, then we're okay. So let's see. We want that the limit of g of x as x approaches -2 coming from the right, and the limit of g of x as x approaches -2 coming from the left. Well, let's see. What is the limit of g of x as x approaches -2 coming from the right? That means all the values of x to the right of -2. So we just plug it in here. So it's 3 times -2 plus 5. That gives us -1. Okay, so what happens here? Well, what's the limit as x approaches -2 from the left? Well, let's just plug in m times -2 squared plus 2. So that's going to give us 4m plus 2. Now, how will the limit exist? As long as these two are equal. So let's go ahead and equate these two. Right? Okay, so we say 4m plus 2 is equal to -1. So we add -2 everywhere. And of course that'll give us 4. Oh, erase. Let me see. Is that correct? Continue. So 4m is equal to -3. Therefore m is equal to -3 over 4. So here we've seen that if m is equal to -3 over 4, then the limit will now be the limit of g of x as x approaches -2 will be equal to -1. See? Because now if we plug in both sides of these two to get the limit, in particular, if we look at the limit of g of x as x approaches -2 coming from the left, then now we substitute, since m is now equal to -3 over 4, then we say -3 over 4 times, of course, -2 squared is 4 plus 2. That gives us a -1. You see how these two match up? Then that's why the limit of g of x as x approaches to from the left and from the right is equal to -1. And what is g of -2? Well, it turns out we just plug it in here because that's where we have the equal sign for x equal to -2, and it's -1. So the question is, for what value of m will make the given function continuous when m is, so answer, when m is equal to -3 over 4. Woohoo! Composition of continuous functions. If f is continuous at x equal to c, and g is continuous, of course, at f of c, then the composition g of f is also continuous. It's just saying that if you have a function f, and then, you know, the value at f of c is its limit value because it's continuous, and then you compose it now and apply g into f of c, then we see that it's also continuous at its composition. That's all there is. That if we compose two continuous functions, the composition is also continuous. And here's an example. Okay, we have that f of x is equal to x sine of x divided by x squared plus 2. And then we have g of x is the absolute value of x. Now remember, the absolute value of x looks like this. And we know that that's a continuous function. Okay? And if we compose these two, then we get this nice wavy function that is always positive because of its absolute value. It's non-negative. Of course, it's going to have that 0 there. At every multiple of pi, because the sine of pi is 0, the sine of pi is 0, sine of 2 pi is 0, I mean the sine of pi, etc., etc. Okay? So we're saying here that if I compose g of f, that's just plugging in here the whole function. So we take the absolute value of f of x, and that gives us this whole thing, x sine of x over x squared plus 2. And you have a continuous function, and this is interesting because it's a rational function, but notice how the denominator will never be 0. So we're happy there because we don't have any problem of discontinuity occurring in the denominator, or whatever would make the 0 denominator, because x squared plus 2 will never ever be equal to 0. And finally, the intermediate value theorem for continuous functions. Okay, it's better if we just look at the picture. It says here that if you have a continuous function on a closed interval, remember it has to be on a closed interval, and if y sub 0 is any value in between the endpoint values, okay, then we know that there must be a c on the domain that will match up y sub 0. Makes sense? Because look, we have this y sub 0 sitting between f of b and f of a. Then, of course, because it's a continuous function, we know that there was a c to begin with that will match up the y value, y sub 0. Okay. So, how do we apply the intermediate value theorem, let's say, in finding a solution of a function? Okay, well, like, say the function looks like this. Okay, and we see that there's our f of a and there's our f of b. And it turns out that f of a is negative, f of b is positive. Then we know that in between a and b, there must be a value c, x equal to c, for which f of c will be 0 because of the intermediate value theorem. When it changes sign from negative to positive, then we know somewhere in between there's going to be a 0 there. So if we set this function equal to 0, by the change of sign, we're guaranteed that there will be at least 1. I mean, it's possible that there will be more than 1 because, you know, you can have a function that wiggles back and forth. You see? So, but in this case, I only had it pass through the x-axis once. That's just the application of the intermediate value theorem. Now, what is the importance of the function being continuous? Well, here we have the function value 0 and then 3 right there. But if we have, say, y equal to 2, and it does not even exist because we have a jump right here, so we cannot use the intermediate value theorem on a discontinuous function, because it does not take on all values between f of 1 and f of 3. Between f of 1 and f of 4. It misses the values between 2 and 3 right there.